All right. All right. So we're just ready to go ahead and do a problem, standard molar enthalpy of formation problem. And this really isn't the problem, but let's kind of look at it, what it says. Basically, we're supposed to write the balanced equation that describes the formation of 1 mole of liquid ethanol. Now, you might be like, well, what's liquid ethanol? Or what's the formula for ethanol? Formula for ethanol has got 2 carbons, 6 hydrogens, and 1 oxygen. Okay, so we talked about the other day where actually you could have a chemical reaction that's describing the standard molar enthalpy of formation if you do this. On the product side, I'm going to put C2H5OH. I think some of you guys have asked, why wouldn't you like put that H with that H? So make C2H6O. They're trying to kind of emphasize that actually this is a hydroxyl group. So anyway, formation of that in its liquid state. Okay. And it goes on and it says from the elements in their standard state at standard conditions. So we need to have carbon. I'll put carbon over here. We need to have hydrogen. And we need to have oxygen. So here's where you need to remember that, of course, hydrogen is a diatomic element. Oxygen, a diatomic element. At 25 degrees Celsius, I'm thinking hydrogen and oxygen are both gases. So I'll put a little G there. See how this works? I'll put a little G there. Okay, looking pretty good. We said the other day, we talked about carbon, and carbon in its solid state actually has 4 allotropes. And the one that is the standard is actually graphite. So actually, I would put carbon as graphite. I guess I should put carbon S as graphite, that particular allotropic form. All right, so we're on our way. So now all I got to do is balance the silly thing. So remember, in the standard molar enthalpy of formation equation, we have to form 1 mole, so we can't change that coefficient. So it doesn't look too bad though. Looks like I need what, 2 carbons, 3 H2s, and since I only need 1 oxygen on the other side, I'm going to have to go with 1/2 of a mole of O2. That's pretty good. And that's it. All right. So like I said, if you're ever asked to do this sort of thing, or write the equation for the standard molar enthalpy of formation of anything, basically just kind of backtrack. What would you need to make it? All right. So this is actually what we came up with. Dun, dun, dun. And it's balanced. And we kind of played a little game on Monday, and we said which of these do not represent the standard molar enthalpy of formation of something. And we said if it doesn't form 1 mole, it's out. Okay. If the reactants are not in their elemental, standard states, in their elemental form, they're out. So this works. All right. So the delta H of the reaction. Now, here's the deal. Do you remember on Wednesday, all of those tables that we looked at? This is Wednesday. On Monday, all those tables that we looked at, you can find methanol or ethanol in one of those tables. So all you got to do is look up C2H5OH. Okay? And I have it appearing in D2 of Appendix D. Actually, I have the excerpt to show you. So the delta H sub F naught means standard conditions, thermodynamic conditions. F means of formation of C2H5OH is negative 277.0 kilojoules per mole. Okay. So here is an excerpt from earlier. Okay, ethanol, yeah. That's where that number comes from. So we haven't really accomplished much. We basically came up with a number. But I think it's good that you recognize whenever you're looking at these delta H's of formation, all of those, you could basically do what we just did and come up with a balanced equation to show the formation of them. Well, this is, though, what we use the standard molar enthalpies of formation for. So do you remember how anytime you see a delta, it's always final minus initial? Final minus initial. So if you were looking at an equation of a chemical reaction, you probably would say final were the products and initial were the reactants. Okay. So actually, and we kind of have a pattern of this in chemistry, coming up with the deltas of things, looking at the summation of the products, which would be final. From that, we subtract the summation of the reactants. Okay, I don't know. It seems like we used the capital sigma before. It just means in math, you add them together. It's a capital sigma. Okay, and so we're going to do an example like this. But basically, this says if you have a chemical reaction and you do not know the overall delta H of the chemical reaction, it said basically focus on the heats of formation of all the products, add them together, and I usually make a little paragraph. Okay, focus on the heats of sum up all the heats of the reaction of the reactants, and make another little paragraph, and then you do one more little subtraction of those two numbers. That's it. The biggest thing is losing track of where your negative sign is. And actually what we're doing here is applying Hess's law, basically. Okay, we're basically saying, I don't care how you get to these things, okay, but if I know the delta 8, or excuse me, if I know one way to get to these and I can add them all together to get the overall reaction of interest, I'm good. And that's exactly what we're doing here. All right. So let's pick on this one. This was the combustion of benzene that I think we looked at before. So let's use the standard molar enthalpies of formations of the products and of the reactants, and let's come up with the delta H for this overall reaction. Okay, so it looks like this. So we would need the tables. Okay. Now, one of the things I said is that if you have something like oxygen that is in its standard state, uncombined elemental form, okay, it's actually the heat of formation, standard molar enthalpy of formation is 0. These other things we just get from the table. That's where they come from. Okay, so now we're ready to do this. So one of the things you're going to see on the next slide is that these, and it said it on when we work this A actually are the stoichiometric coefficients of the products. So that A will be 6 moles of CO2. That A will also in one term be 3 moles of H2O. This B right here will be these stoichiometric coefficients. So here we go. Like I said, I kind of have like 2 little paragraphs, not really very paragraphs, but kind of separate it like that, and then I have one last subtraction. Okay, so the summation of the heats of formation of the enthalpies of formation of the products looks like this. We have 6 moles of CO2 from the balanced equation. For 1 mole of CO2, the standard molar enthalpy of formation is negative 393.5 kilojoules. So 6 moles CO2 times negative 393.5 kilojoules per mole of CO2. Of course, the moles of CO2 cancel out. We're left with the energy. Okay. The next term would be our water term. So we have 3 moles of H2O times negative 241.8 kilojoules of energy per mole of H2O. That was from the table. So now we got basically the energy associated with the product side. Go ahead and make sure that you're still applying the rules of rounding. So the stoichiometric coefficients of 6 and 3 bring no uncertainty. Okay, so it's kind of like just basically adding a bunch of numbers. We add, we round according to decimals. So we're allowed 1 decimal. So on my product side, I have a whopping negative 3,086.4 kilojoules. All right, and I set that aside, and then I move on to my reactant side. And it looks like this. There was 1 mole of C6H6. In the table, we know that the standard molar enthalpy of formation is positive 49.0 kilojoules per mole of C6H6. That came from the table. The next term is my favorite. I would still suggest you write it down. I think I did. Yep, I did. We need to turn our attention to the other reactant. 15 halves moles of O2. Of course, the standard molar enthalpy of formation of O2 in its gaseous state is 0. Okay, sometimes students don't want to put that there, but I think we should. Then we go ahead and I can do that math, right? So the summation on the reactant side is simply 49.0 kilojoules. But I know I've already said it, but it's very easy to forget how you do the last step. So basically we have those two terms and now we're going to subtract. So it's always final minus initial, it's products minus reactants. So here we go. For the overall reaction of interest, drum roll, we would take that negative 3,086.4 kilojoules that we got from the product side, and from that subtract the positive 49.0 kilojoules of energy we got from the reactant side. And we come up with a change in enthalpy for the reaction of interest is negative 3,135.4 kilojoules of energy, and that's it. So there you go. That's what you use the standard molar enthalpies of formation for. And we're actually in Chem 2, we do a really similar thing with coming up with the change in Gibbs free energy, looking at the standard Gibbs free energy of formation of the reactants and the products. All right. So now these will be due on Friday. Fabulous Friday. And I actually had these from last year. Some I have from last year, some I do not. And they look like this. The first one, I'm just going to show you basically A. But notice these are balanced for you, aren't they? Yes, thank you. They are balanced. So you're supposed to come up with the heat of the reaction of A and the heat of reaction of B using the standard molar enthalpies of formation of the reactants and products. You don't have, you don't have anything like you had the O2 in this, where it's 0, but they're not too bad. Come back here. All right. So we're going to use this this equation to knock it out. And so, like I said, I kind of did the first one for you. So I kind of make a little paragraph for the products. Stoichiometric coefficients are 1 for the C2H6 and 1 for the CH4. I look up the value on the table for the C2H6 and the CH4, and voila. And then I need to turn my attention, or you need to turn your attention to the reactants. Again, they're there in 1 mole quantities. Look up their value. Oh, I guess there was one. Yep. H2, standard molar enthalpy formation is 0. You did have one. And then my last little bit is you subtract, basically, you take the purple and you subtract the green from it. Okay, so it's the products minus the reactants. And then you have it, heat of reaction. For B, similar to A. And I think for question 80, similar to question 79. And that's it. They're kind of fun. Just make sure they should be balanced. Yep, that one's balanced again. It's weird to see coefficients of 1. You're like, really? Yes, that is balanced. Okay. So let's go on to last part. All right. So we talked, gosh, way back at the beginning of the semester, weeks ago, about the three main physical phases we're worried about. You know, physical phase, because matter can either be a solid, matter can be a liquid, or matter can be a gas. And we talked about that. Those are, when we talk about phase changes, that's what we're talking about, okay? And you guys already know that if you take an ice cube and you want it to melt, well, if you put heat to it, it's going to go from a solid to a liquid. That's exactly what we're talking about. Okay, exactly. So in physical science or in chemistry, there's this thing where if you are breaking bonds, and actually when we're melting an ice cube, the bonds we're breaking are those, I think I talked about those kind of intermolecular bonds between the water molecules. Those are the bonds we're breaking. It requires energy. Actually, when you're breaking a chemical bond between the oxygen and the hydrogens, that also would require energy. But did we know this? This is a little less intuitive. When bonds are formed, energy is released. It almost sounds like it should be a rap song. When bonds are formed, energy is released. So if we take the example of an ice cube, okay, when water goes from a liquid water to a solid ice cube, bonds are formed, okay, energy is released at that time. And we've been all talking about thermodynamics, tracking energy. That's the energy we're going to track now. Energy associated with a phase change. Some things require energy, endothermic. Some things actually release energy. It's going to be exothermic. Okay. So, oh, yep. Let's see. I already have this pulled up. I think we looked at this before. But again, it takes energy to break a bond that's connecting things, whether they're connecting atoms in a molecule, or whether they're connecting molecules as an intermolecular bond. And when bonds are formed, energy is released. This is just to kind of emphasize, I have to do this, the whole, the three physical phases of matter. I make sure we're all on the same track. So I think I got this to loop. I mean, this says a lot, right? I mean, if we would all think of matter this way, we would all get way down the road. Okay, when matter is in its gaseous state, okay, one of the things about it, it basically has no bonds. It's free. Has a lot of kinetic energy, right? When matter is in its solid state, it has a lot of intermolecular bonds. It basically has not much motion, but all matter has motion. Okay, so that's kind of what that's emphasizing. Okay, so put another way. I have the physical phases kind of like from left to right, solid and liquid and gas. Okay, and consistent with, you know, what you know about things. To go from a solid to a liquid, like an ice cube to liquid water, we would break bonds. To go from a liquid to a gas, again, we would break bonds. Okay, and actually these are phase changes that we call, they're endothermic phase changes. Now, if we go from right back to left again, okay, if we take a gas and have it liquefy, that we call that, of course, condensation, actually energy is going to be released. And when we, in meteorology, boy, that hurricane kind of fizzled out, didn't it? That Hurricane Patricia? Thank goodness, right? But in meteorology, when we talk about the energy associated with a storm, it's basically this. Basically, all that energy that's released as water vapor condenses and forms liquid water. Lots of energy. As a liquid solidifies, energy is also released. These we would call exothermic processes. All right. So the animation I showed you kind of reminded us how this works with the three physical phases of matter. Any matter in its gaseous state has a high amount of kinetic energy, low degree of intermolecular bonding, increased because of its increased motion. Okay, over here, if matter is in its solid state, although all matter has motion, it has less kinetic energy, okay, least amount of kinetic energy, decreased motion. Then we have this. Did we cover this in, I think, earlier this semester? Where basically we can, again, take the three physical phases of matter, solid, liquid, and gas, and we can talk about, with regard to their size and shape. If something's a solid, it has what we call definite size and definite shape. So like I could have brought a beaker in here, and I could have had some of those colored blocks that I think you guys used earlier in the semester, and put those blocks in my beaker. And those blocks would have stayed the same size and volume that they are, even though I put them in a beaker. I could take a liquid on the other hand and pour liquid into my beaker, and it's actually going to take on the shape of the beaker. So we say liquids have indefinite shape, but the volume of the liquid should stay the same as long as the temperature is the same. And last but not least, when it comes time for gases, they're the most fun, right? A gas has got all that crazy motion associated with it, so whatever volume you give it, it will bounce around in. I just think gases are wonderful. So its volume is indefinite, and also its shape is too. And all of that with regard to size and shape, it's all related to how much intermolecular bonding it has. And in Chem 2, we're going to kind of pick up and look closely at the intermolecular bonding. Okay, so just the chemical bonding. Okay, so let's make sure we're all on the same page with regard to physical phase changes. Something goes from a solid to a liquid, we would call that melting. That's endothermic. If something goes from a liquid to a gas, we would call that evaporation or vaporization. It's always kind of nice when you're like, oh, I got that. If something goes from a liquid to a solid, we would call that freezing. And if something goes from a gas to a liquid, we call that condensation. So again, already today is I could draw a line here in the sand, and I could say that these are endothermic, and I could say that these are exothermic. And what do we know about those? Yeah.
This is independent of temperature, correct? I mean, if you have something freezing going from liquid to solid, it doesn't have to be below 32
Right.
So
Yep. As long as the phase change is occurring, you put on blinders, whatever the temperature is that it can occur at. That's, yep, that's a good point. Those are exothermic down there. So, what do we know about these? We said that something that's endothermic, we were going to give that a positive delta H. Does that seem right? And anything that's exothermic, we were going to give that a negative delta H. And that's exactly what you're going to see. Totally. Okay. All right. So, let's watch a little video. Continue to remind myself, you can have evaporation way at temperatures below the boiling point temperature. Something doesn't have to boil in order for you to smell it, for instance. Okay? Gasoline, you put gasoline in your car. Do you ever smell the gasoline? You know? But it's liquid, but it's gas. It just is what we say very volatile. Has a high volatility to it. Okay. Let's see if this will go. Okay, now there was one phase change that actually I want to address, and it's the phase change that skips the liquid state. So here we have something going from a solid directly to a gas, and actually we can have the other thing where something goes from a gas directly through the solid and skips the liquid stage. I'm hoping tomorrow to bring some dry ice just because I want to kind of have it for to make the lab look all weird. We'll see. But what dry ice is basically carbon dioxide that they have compressed and cooled to the point of carbon dioxide being a solid. When you buy dry ice, okay, you buy it and you're hoping that it's going to cool things down. Well, here we go. It's solid. You put it right here. And dry ice, you'd see that kind of smoky sort of thing. This was another one for me too. I'm kind of embarrassed to say this, but that smoky sort of stuff that you see, that's not CO2. Actually, that's in the vicinity of the coolness. That's actually water vapor that's condensing. I thought that's kind of cool too. I always like, oh, it's carbon dioxide. No, it's actually water vapor, but we can call it carbon dioxide. The thing is, it's really cold, right? Dry ice is really cold. It's really cold because to go from a solid CO2 to gaseous CO2, is that endo or exothermic? Endo. You have to put energy in, okay? Very endothermic. And where's it going to get that energy? Well, if you're holding onto it with your hands, it's going to get the energy from you. It's going to get the energy from the surroundings. So anyway, we call that actually sublimation. When something skips the liquid stage, okay? And it doesn't just happen with CO2 like dry ice that you buy. It also happens in your freezer, different times of the year. If the old-timey where you had to make your own ice cubes, so you'd have a plastic ice tray, you fill it up with water, and then you put that water that's liquid in your freezer to go ahead and freeze. Well, if you were kind of waiting for a couple weeks before you used your ice cubes, what would happen is you would go back and you'd be like, oh my gosh, where's my ice cube? Okay, basically what happened is it froze like you thought it should, and then over time it basically, I think it's freezer burn too, has related to freezer burn. Basically that solid went to a gas in your freezer and then deposited on other things. Freezer burn, something like that. Okay. All right, so I have a little video. Oh, by the way, then the other one, I think it could be called sublimation, but I've heard it called more deposition, or I've heard it called deposition, not condensation. But for instance, in meteorology, we talk about frost. Okay, so like you go to bed at night and you wake up in the morning, and it's going to happen one of these days, right? Your little green grass is going to have frost on it. Okay, so think of how that frost got there. If it's been, oh, let's say it was, 25, 30 degrees, okay? How did that frost get there? Well, basically, water went from being a vapor directly to being a solid. Okay, is that not cool or what? So I would call that deposition. So the little video we have here shows you iodine. Now, iodine is one of those halogens, and it's one of those diatomic elements, so it's always I2. So, here's the video. All right. Sublimation and deposition. So let's talk numbers. That's all been kind of qualitative, kind of. All right, so again, endothermic would be putting energy in, and why would we put energy in? Well, we're breaking bonds, and when we break bonds with phase changes, of course, you're talking about your melting and your evaporation, okay? You're also breaking bonds when something goes from a solid directly to a gas. You're breaking bonds. Energy is put in, and like I said, that's why when your dry ice, which is solid carbon dioxide, that's why it gets very cold, because it's endothermic. It's requiring energy. Then exothermic, exo meaning exiting. So energy is released, and energy is going to be released when bonds are formed. We're talking about those intermolecular bonds here. And intermolecular bonds are formed during freezing. Of course, freezing means when something is going from a liquid to a solid. Condensing means when something is going from a vapor or a gas to a liquid. And this is where I really like the word deposition better than sublimation here. We say that water deposits, I think. All right. Can I see your notes? See how far we are? I think we'll go ahead and stop there a little bit early, and we'll pick up here on this slide on Friday.
On the phase change slide?
Yeah.
Okay.
Yeah. Yep. Then we'll talk numbers. It'll all kind of work together, I think.